So at this point, we have seen the definition of the Z-transform and several Z-transforms of different functions. And then we have seen the properties, several properties of the Z-transform. Now, the last part of the lecture will cover the inverse Z-transform. So we have seen how to convert a sequence in the Z-domain, but now we have to see how to go back to the sequence domain, to the time domain. Otherwise, this tool is not useful if we cannot actually go back to the sequence domain, so the real world domain. Okay, so the fact that that a mapping, that the Z-transform is actually invertible, it means that given a Z-transform, we can recover a unique sequence x of k. Okay, so invertible means that to a Z-transform, it is associated a unique sequence x of k. Otherwise, the tool is pretty unuseful, because if given a Z-transform you can recover multiple different sequences, then you don't know actually what is the real result. However, you have to notice that this doesn't mean that we recover a unique continuous time signal. The reason is that while there is a one-to-one relation between the Z-transform and the sequence, so given a Z-transform there is a unique sequence, we saw in the previous discussion that multiple, actually an infinite number of continuous time signals are actually associated to a sequence, because we don't have any information between the sampling times. Okay, so to make this clear, there is a one-to-one relation between the Z-transform and the sequence, but then to the sequence there are associated an infinite number of signals. Okay, so let's explain this with an example, and we consider the Z-transform of cosine of omega capital T, K. Okay, so this is the following sequence. We saw that the Z-transform will be equal to this term. Okay, so we saw this Z-transform already. We know that this will be the Z-transform. Now let's set the sampling time as 2 pi over omega. Okay, so we pick this sampling time and we see what happened. Okay, if we pick this sampling time and we replace t in there, then we get that the Z-transform of cosine omega t k is actually equal to 1 minus z power minus 1, and then the cosine of omega t when t is equal to this is actually the cosine of 2 pi, that is 1, and then we have 1 minus 2z power minus 1, cosine of omega t, that is 1, plus z power minus 2. And now this is equal to 1 minus z power minus 1, and this is actually can be factorized, and is 1 minus z power minus 1 squared. Okay, so this is the square of this term. And so this is actually equal to 1 divided 1 minus z power minus 1. And we know actually that this is the Z-transform of 1k, where 1k is the unit step function. So to understand what's going on, let's sketch the function. Okay, so let's put here capital T, here 2 capital T, here 3 capital T. Okay, and then we have that this function here with this sampling time is doing this. Okay, and we see that at this point we have that the value of the function is 1, at this point the value of the function is 1, at this point the value of the function is 1, and so on. Okay, so what happens is that the continuous time sequence is the cosine, but we are sampling always at this with this period, with the sampling time equal to 2 pi over omega. And what happens is that what we are sampling is only 1, 1, 1, 1. Okay? So we see that there are an infinite amount of different functions that can go through these points. So if we look at this, we may think that actually the function, the continuous time function is this one. Okay? But we don't know. We don't know if the continuous time is this one, the continuous time function is this one, or is this one. So you see that in this case, the Z transform is this one. Okay, so you can write it as you wish. You can write it like this, or you can write it like this. You can write it like this. Okay, so these two expressions when t is equal to pi over omega are the same. Okay, so there is only one Z transform. Okay. And to this Z transform, there are associated only one sequence. The sequence is this one, that can be represented with this, or it can be represented with this term when t is equal to pi over omega. However, the continuous time function is unknown, because it may be the straight line as the continuous time version of this function, or it can be the cosinusoid as the continuous time function version of this function, but we don't know. Okay. Okay, so said this disclaimer, what we are going to see now is several methods to compute the inverse Z transform. And in particular, we'll look at 4 methods. The first method that we study is the direct division method. So the direct division method is based on the definition of Z transform. So we know that the Z transform is actually the sum of the values of the sequence, all the values of the sequence multiplied each time for a different power of Z minus 1. Okay? So the Z transform is actually, by definition, equal to this term. So it means that actually the first value of the sequence, x of 0, is equal to the first number, x of 1 is this number, and so on. So the idea behind the direct division method is to write the Z transform in this form so that we can see the sequence and then try to infer what is the rule that produces these numbers. You may already imagine that this is actually very hard, and only in special case you can actually infer, looking at the values, the rule that produce these numbers. So this direct division method has a limited application. Okay? But let's look at it. The first step to compute to use the direct division method is to write the Z transform in this form. Okay? So let's start with a Z transform. So let's look at an example. Okay, so we start with this Z transform. First step is to divide the numerator and denominator by Z so that we obtain this expression. And then we have to compute the division between this polynomial, and we get this expression. You may not remember how to compute, how to perform this division, so let's look at this example together. So what you want to do is to divide 10z power minus 1 plus 5z power minus 2, and you want to divide this by 1 minus 1.2 z power minus 1 plus 0.2 z power minus 2. Okay, where 1.2 is equal to 6/5, 6 divided by 5, and 1 divided by 5 is 0.2. So you want to compute this division, so we write the result over here. So to do so, we take this number and we divide it for this number, and we get 10z power minus 1. And then we multiply the result by this, and we get 10z power minus 1, and then minus 12z power minus 2, and then we get plus 2z power minus 3. And then we do the subtraction between this number, and here we get 0, and here it's 5 minus 12 is 17z power minus 2, and then here we get minus 2z power minus 3. Okay? Now the next step is to divide this polynomial for this polynomial, and we get the first, the 17z power minus 2, divided by 1, and so we get plus 17 z power minus 2. And then we multiply this term by this term, and what we get is 17 z power minus 2, and then we have minus 20.4 z power minus 3, and plus 3.4 z power minus 4. Okay? So when we multiply 17 z power minus 2 for this polynomial, we get this polynomial. We do the difference, and here we get 0, and there we get 18.4 z power minus 3, and here we get minus 3.4 z power minus 4. And then we continue in this way, okay? And in this way, you see that you obtain the values that are in this sequence. Now, you see that what we obtain is 0, 10, 17, 18.4, and so on. Given these numbers, it's very difficult to understand which sequence, which x of k produce this number. Let's look at a different example in which we can actually infer the function that produces the sequence that produces those numbers. So let's look at this example in which the function, the z transform that we want to convert is tz divided z minus 1 power 2. So we expand this denominator, and we divide and multiply by z. We divide and multiply by z, by the z square, and we obtain this expression here. And now we do the division between the numerator and the denominator. Okay, we apply the same rule that I just explained. So we take this, we divide it by 1, and we write the result here. Then we take this result here, and we multiply it for the polynomial. So we obtain tz power minus 1, and this will simplify with this when we do the subtraction. This is because by construction the division works like this. And then we multiply this term by this term. And we see that multiplying this by this, we obtain minus 2 tz power minus 2. And then we obtain also another term over here. When we do the subtraction between this term and this term, we will get, okay, as I said, 0 for this. And for this term here, we actually get 2tz power minus 2. And this will be the next term of the sequence, and so on. So again, I'm not going to write it down, but you can apply the division as I explained just before. And we obtain this sequence. And you recognize that this sequence is actually the sequence produced by k times t. Okay? So you see that only in very special cases you can actually look at the sequence and see, okay, this is actually the sequence produced by this expression, by this function. The next method that we see is the computational method. So the computational method is a method that is very useful to interpret the z-transform when you want to implement a control law using a microcontroller. Okay? And the computational method is what you use, for instance, when you use MATLAB to try to see to generate the sequence, okay, that produced a certain z-transform. So to explain the computational method, we use an example. So the example is the following. We have this function, and the first thing that we do is to note that we can write this function as the same multiplied for u of z when u of z is equal to 1. Okay? This implies that u is actually the sequence producing u of z is given by this expression. Okay, this is obvious because the z transform of this sequence is equal to just the first term, and so u of z is equal to 1. Okay, because then you multiply 0 by a power of z, and you always get 0. So now the next step, I will show it at the board. So we multiply and divide by z power 2, okay? And so, and multiply both on the left and on the right for the denominator. So what we obtain after that we do these two operations is 1 plus b1 z power minus 1 plus b0 z power minus 2 x of z equal a1 z power minus 1 plus a0 z power minus 2 for u of z. Okay? Now we use the shifting theorem, and so we see that when we compute the inverse z transform of this expression, so we use both linearity and the shifting theorem, then we get x of k, this times this, plus b1 x of k minus 1 plus b0 x of k minus 2. This is equal to a1 u of k minus 1 plus a0 u of k minus 2. Now let's rewrite all this sequence for adding 2 steps. Okay, so here instead of x of k, I write x of k plus 2 plus b1 x x of k plus 1 plus b0 x of k. So we just translate everything of 2 k's. Okay, and so we get this expression here. That is the expression that you have on the slide. So just to write it as in the slide. So how does it work now? Now, basically, this expression is an iterative expression, and if we know x1 and x0, then it's possible to compute the next xk for all values of k greater than 2, okay, greater or equal than 2, okay? So to actually do this, we need the values of x1 and the values of x0. So we first want to compute the value of x0. To do so, we replace k equal to minus 2 in this expression. So doing so, we obtain this expression over here, where you see that this number and this number is 0 because the value of k is negative, as is this one and this one. So you get that all this expression is 0, part of s of 0, but obviously x of 0 is equal to 0, and then we get this expression. The next value that we compute is x of 1. To compute this, we replace k equal to minus 1. For k equal to minus 1, we get this expression over here. Then we remember that x of 0 is 0, x of minus 1 is 0, u of minus 1 is 0, u of 0 is not 0, but is equal to 1, so actually x of 1 is equal to a1. Now we have x0 and we have x1, and we can compute in an iterative way all the values of the sequence. Because basically we have this law, we have x0, x1, we have u0, and all the u for all values of k. Then to compute x2, we just replace k equal to 0 in this expression. We replace the values that we have, and we get this expression. x3, and we get this expression, and so on. Okay? The reason why this is useful is that this can be implemented at the computer very, very easily, and you can implement it in MATLAB. So let's look to an example. So this is the example that we see. So we apply the procedure that we have shown, and we obtain basically this expression over here. So this is the rule that is true for all values of b1, b0, a1, and a0. So in our code, what we write is, first of all, we set the values of a0, a1, b0, b1, and so on. Then we set the initial values x0 and x1 as we computed here. Okay, so x1 is equal to a1. u0 is 1, and u1 and all the u's is actually equal to 0. And then we compute we write an iteration for 18 values. So we count from 1 to 18, and we repeat this code. So the next x is equal to 2, and we compute it basically writing that x2 is equal to, and we bring all the terms on the other side. Everything is known. We get the value, the new value of x. We store it x2. We store it in x. And then we set, we update the values of the variables, and we repeat the code. Then we plot this in MATLAB, and we get this nice expression over here, with a nice graph over here. So this is basically what we see here, is the sequence, x of k that produce this z transform. And this is the sequence for 20 values of k, for k equal to, from k equal to 0 to k equal to 20, okay? And this is also the, if we want to interpret it, as the response of this transfer function, if this we interpret as a transfer function, when the input to the transfer function is u of z equal to 1. Okay, that, as we've shown here, u of z equal to 1 correspond to the unit impulse. Okay, and so we get basically this interpretation of the graph and also the sequence, and we can generate all the values of the sequence. In this case, we see that actually the sequence is converging to 0. Okay, also this method is not useful to actually find a closed form, to find a closed form for the sequence generating the Z transform. The third method to compute the inverse Z transform is the partial fraction expansion method. So probably you already seen this method when working with the Laplace transform. And even before, you probably did partial fraction expansion when trying to solve some type of integrals in your course of calculus or in high school. So the partial fraction method allows us to find a closed form of the inverse Z transform, so of the sequence. So this is the first method that we see that allows to find the original sequence. So we present the method divided in two different cases, one simple case and one more complicated case. So the assumption is that we have a Z transform here that can be described in the following way. So we have a fraction of polynomials in which the assumption is that m is less or equal than n. Okay? So the degree of the numerator is less or equal than the degree of the denominator. This is not a strict assumption. It's not an assumption that makes us lose generality, because if that's not the case, then we can actually factorize the numerator and bring it basically outside. So in this case, we can write this fraction in the following way. So we factorize the denominator in the factors that produce that denominator. And in the simple case, so the first case that we see is the case of simple poles. So the case of simple poles is the case in which we have that the pole pi is different from the pole pj. So all these numbers here at the denominator are different. So the pole is that number that replaced to the z makes this monomial equal to 0. So the pole of this monomial is actually p1. The pole of this monomial is p2, and so on. And this is, in this case, we have that all these poles are different, and that pi is different from 0. Okay? Then we consider the function xz divided by z. So what we are expanding is not the function xz, but is xz divided by z. This is important, okay? So this is an important step. You have to remember that when you use the partial fraction method, you have first to divide the function by z. The reason is that if you don't do that, the partial fraction becomes more complicated, and the function that you obtain, you may not be able to recognize what you're going to obtain. In this case, instead, if you divide xz divided by z, then you obtain this expression. Okay, so you can write this fraction in this way, where you have all the poles of the original function. You have an additional pole due to the fact that you divided by z, and then at the top you have the residuals. So the aim here is to find these residuals, so these numbers are 0, are 1, are 2, and so on, such that the sum of these fractions is actually equal to xz divided by z. Okay? So to compute these residuals, we can use this very simple formula here. Okay? So R0, so the residual associated to z, is just the z transform x of z computed in z equal to 0. For all the others, the residuals can be computed in this way. So the residual associated to the pole pi is computed as the limit with z that goes to pi of the product z minus pi times xz divided z. Okay? So the reason why this is the definition of the residual is quite simple, and maybe we can see it quickly at the board. So we have that xz divided by z is equal to r0 divided by z plus r1 divided z, let's see, minus p1 plus r2 divided z minus p2 plus and so on. Okay? So let's say that we want to compute this residual. So the idea is the following. We multiply both sides for z minus p1. So we have z minus p1 that multiplies x of z divided z. And here we have z minus p1 divided z r0 plus r1 plus r2 z minus p1 divided z minus p2 plus and so on. Okay? Now you see that if z converges to p1, okay, so basically we compute the limit with z that goes to p1 of this term, okay, we have to compute the limit also on this other side, and we see that this term will converge to 0 because we are replacing p1 here. This term will converge to 0, okay, and this will be true for all the terms apart this term. So this term is actually equal to the limit with z that goes to p, in this case p1, okay, of this expression. Okay? Okay, now that we have found the residuals in this expression, we multiply both sides for z. In this way, we obtain this expression here, where we have r0 plus, and then all the expression that we found before multiplied by z. And now we actually multiply and divide by z so that we can actually write these in this form. Okay, so we obtain the form in z power minus 1. And now we recognize that actually these are z transforms that we know. They are simple z transforms. In particular, the z transform of this type of term, okay, is the z transform of the power function. So we see here that the z transform of a power k is equal to this type of function. So you see that actually this, for instance, if we look at this particular fraction here, this is equal to r1 times p1 power k, using this expression here. Okay? And the other transform that appears is the transform of 1, because r0 is basically r0 times 1. Okay? And we recall that the transform of 1 is the z transform of delta of k, where delta of k is 1 for k equal to 0 and 0 for all other k's. So it's that function that has that is 0 for every k, apart for k equal to 0. Obviously, that's by definition. If you apply the definition of z transform, you will get that the z transform of that function is actually 1. So, using these two transforms, we can write that x of k is equal to the sum of these terms. Okay? So you see that this is a way that allow us to compute in a pretty mechanical way the sequence that generated a certain z transform. Another thing to notice is the fact that if x of z has real coefficients, and that will be the case for all the functions that we study, then complex poles appear in conjugate pairs, okay? And the corresponding residuals will also be conjugate pairs. So this means that you can put together these pairs and get real terms, okay? So if x of z has real coefficients, x of k will also have real values, and you always have to obtain a sequence that has real values. Okay, now we have seen that this is the transform, so this system works when the PIs, the poles, are simple, so are all different. What happens when you have a repeated pole? So let's assume that in this case we have only one pole, but this pole is repeated n times. So we do this usual trick of taking x of z and we divide it by z, and we want to find the residuals for this decomposition, okay, for the sum of this expression when we have the pole p, so only one pole, but this pole is repeated n times, okay? So in this case, the formula is more complicated, and the formula to compute the residual associated to this pole is given by this expression. So basically, you have to take the function here, you have to multiply it for the highest power, then you have to take the derivative corresponding to which term you want to isolate, take the limit, adjust the coefficients because you are computing a derivative, and you will get the term, okay? Also in this case, the explanation of this is pretty straightforward. So the idea is the following. We take the function and we multiply for the highest power. So this will mean that if we look at this power here, this term will disappear, and all the other terms will get at the numerator at z minus p power something, okay? Here, this one will not appear here, but here you will have, for instance, z minus p power n minus 1, and here z minus p power n minus 2, and so on, okay? Then to select the correct residual, you can compute a derivative, because when you compute the derivative, the degree of all the powers will decrease by 1, and the one that is constant will disappear. So if you don't compute the derivative and you compute the limit, then all these terms will disappear apart this term that does not multiply z minus p. But if you take the derivative, so you take the first derivative, then what happens is that this is constant and will disappear, and all the other terms will decrease, so the term, the residual r(i) n minus 1 will become constant, will not multiply z minus p, and when you take the limit, you will actually isolate that term, and so on. So this is basically the idea behind this formula. I'm not going to spend more time on this. This is a standard formula, and you can find it on books of calculus, basically. So let's do an example to explain actually this. Okay, so the first example is quite easy. So in the first example, we have the function x of z equal to this expression. So the first step is to divide by z. So we take the function and we divide by z, and we see that z appears here. Okay. Now what we want to do is to divide these in factors. So let's do it at the board. So you want to write x of z divided by z as r0 divided z plus r1 divided z minus, and the pole is 1, okay, plus r2 divided z minus, and the pole is 1 over 5, okay? So now we want to find r0, r1, and r2 such that this is true, okay, where xz divided z is 10z plus 5 divided z minus 1, z minus 1 over 5. So this is the case for simple poles, and so this is quite easy to do. So r0 can be computed here when you multiply for z, so this is not here anymore, and then we replace z equal to 0 and see what happens. So it's 5 divided minus 1 times minus 1 over 5. So it's 5 divided 1 over 5. Okay, so it's 5 times 5, so it's 25. Okay? Now R1 is computed multiplying this for the pole z minus 1 for this monomial. So this term will disappear, and then we have to replace the pole, and the pole is 1. So it's 10 plus 5 divided 1, this thing is not here, times 1 minus 1 over 5. So 1 minus 1 over 5. Okay? So this is 15, divided 4 divided 5, and so this is 75 divided 4, okay? Then the last residual, R2, is again computed multiplying this by this pole, so this disappears, and then you replace 1 over 5. So is 10 times 1 over 5 plus 5 divided 1 over 5 times 1 over 5 minus 1, that is minus 4/5, okay? So we do this, 10 divided 5 is 2, so on the numerator is 7, and here it's minus 4 divided 25, okay? So we have 25 times 7 divided minus 4, so it should be minus 175 divided 4, okay? So you see, actually, if we go back to the slide, that this is the residuals that we obtain here. Now what we do is that we multiply both sides for z, and we obtain this expression. And now we just, okay, we also divide and multiply by z to obtain this version here. And now we just recognize the z transforms, the basic z transforms, the z transform of the constant, that is the delta, and then the z transform of the power. And so you get this, where the power is 1 over k, because the pole is 1, and here is 1/5 over k, because the pole is 1 over 5. Okay? Let's look now at a more, bit more complicated example. In this other example, what we have is that once that we factorize, we divide by z and we factorize, we obtain complex poles. So we compute the residuals, so the procedure is the same, so these are simple poles. We compute the residuals and we obtain this expression over here, okay? So this is the result once that the residuals are computed in a similar way as we have just done. Then we multiply both terms for z, and we obtain this expression here, and then we multiply and divide by z, so that we obtain the expression in z power minus 1. Now, I want, from this expression, we want to obtain the sequence, and now let's do this at the board to see how we obtain this. So by reading the expression that we have on the slide, we know that the sequence will actually equal to 2 delta k minus 1 plus 4j 1 over 2 plus 1 over 2j power k minus 1 minus 4j 1 over 2 minus 1 over 2j power k. Okay? So we obtain this just by reading what is already on the slide. Okay? So we computed the residuals, we found the partial fractions, and from that we obtain this expression. The problem of this expression is that the numbers, the values that appear, are complex. And we don't want this because the original z transform is real valued. So we know that we can write this in a real valued sequence. Okay? We want a real valued sequence because we want a real signal, not a signal that doesn't exist. Okay? So we have to try to rearrange these terms in such a way that we obtain actually the a real sequence. So we don't touch this. And here we have 1 plus 4j. And now we want to write this in polar form. So the absolute value of this term is 1 over square root of 2, okay, times, and then the e power j, and then we want to put the angle over here. And the angle associated to this is pi over 4, and all this is power k. We do something similar with the other expression. Obviously, the absolute value of this is the same, so it's 1 over square root of 2, and the only thing that is different is that the angle would be minus pi over 4, and this is power k. Okay? Now, we try to put together some of the terms. Okay? So we put together, so as usual, we leave this as it is here. And now we see that we have minus 1 and minus 1 over here. So we have minus, so we factorize 1. So minus 1 that multiplies what is inside. So the square root 1 square root of 2 that appears in both cases, power k. And then here we have e power j power pi over 4 k plus e power minus pi over 4k, okay? And then the other term that we have is minus 4j, okay? So let's write it minus 4j. And what remains is, again, 1 over square root of 2 power k. And then we have e power j power 4, j pi over 4k. And here we have the opposite sign because we are factorizing minus 4j, but there is the minus here. So it's minus e power minus j pi over 4k. Okay? So we obtain this expression over here. Now what we do is we recognize that we have almost obtained cosinusoids and sinusoids. So we actually cosine and sines. And so what we do is that we divide by 2 and multiply by 2 here. And here we divide by 2j and multiply by 2j over here. Okay? Now we recognize that this term over here is the cosine, and this term over here is a sine. So we can write this as 2 delta k, and then we have minus 2 times 1 over square root of 2 power k times the cosine of pi over 4k. And here we have minus 4j times 2j, so it's plus 8, 1 over square root of 2 power k, sine of pi over 4k. And this is the expression that you have on the slide. The last method that we see is the inversion integral. So the inversion integral is the most general technique for finding the inverse Z transform, okay? And it's based basically on the definition of the Z transform and the fact that that operator is actually an inverse operator that is defined using this inversion integral. So the problem of the inversion integral, if you want, is that the expression is quite scary because this integral is actually a complex integral, okay? It's an integral on complex variables, and this means that computing this integral is quite complicated. However, there is a very useful theorem of complex analysis, complex calculus, that tell us that in some cases, and in particular, when the function xz times z k minus 1 has a finite number of poles, p1 of order q1, p2 of order q2, and so on, okay, with the pi different from 0 for all I, then there exists this expression, this relation between the inversion integral, so x of k basically, and these terms, R1, R2, and so on, where Ri, these terms, are actually computed using this formula, okay? So, what does it mean? Okay, it means that this inversion integral, that in general is difficult to compute, in many cases, and basically all the cases that we will see, actually there is a trick to compute this integral, and this trick is given by this expression, these residuals, R1, R2, and so on, where the formula to compute these residuals is given over here, okay? So the expression, the assumption is that the formula is valid only when xz times z power k minus 1 does not have poles at the origin. So it's important that we are not talking about x of k, but it's, sorry, x of z, but it's x of z times z power k minus 1 that doesn't have to have poles at the origin, okay? So if you are interested actually in the theorem that justify this, you can find this in a book of complex calculus, okay? But if we are just interested on the practical aspect of this, I have to say that this formula is very useful, and it's one of the best way to compute the inverse Z transform of a sequence. To convince you of this, we make an example now. Okay? So the example that we do is x of z equal to z power 2, z minus 1 power 2, z minus e power minus 80. Okay? So how do we compute the inverse Z transform of this function? So first of all, we compute x of z times z power k minus 1. Okay? So the denominator will not change, it's the same. The numerator will be z k minus 1 times z power 2, and so it will be z k plus 1. Okay? So we see that this function does not have any pole at the origin. It means that there is not a z at the denominator. Okay? So we can apply the formula, and we want to compute R1. Okay? For me, R1 is the residual, okay, that is associated to the pole e power minus 80. Okay? Okay, so let's compute this residual using the formula. So if we look at the slide, the formula tells us that we have to take the function xz times z power k minus 1 that I wrote at the board. We have to multiply for z minus the pole power the degree, the order of the pole. But the order of this pole is 1. So I have to do z minus EAT power 1 times zk plus 1 divided z minus 1, z minus E minus 80. Okay? Now we have to compute the derivative of the order of this pole minus 1. The order of the pole is 1, so 1 minus 1 is 0. The 0 derivative is actually no derivative, so we don't have to do any derivative. Then we have to compute the limit. So is the limit with z goes to a power minus at of this expression. And then we have to multiply for this coefficient. Again, the order is 1, so it's 1 minus 1 is 0. The factorial of 0 is 1. 1 divided by 1 is 1. So it's just this expression over here. So let's compute this residual. So you see that this expression and this expression will cancel. And then we replace e power at in this expression. And so we see that we obtain e power minus at power times k plus 1 divided e power minus at minus 1 squared. Okay? So that's the first residual that we obtain. Now let's compute the second residual. So the second residual is the residual associated to the pole 1. Okay? So again, we start first, we have to multiply the function for the pole. So z minus 1 power 2, zk plus 1 divided z minus 1 square, z minus e power minus at. Okay? So let's look again at the slide. I'm multiplying for z minus 1 power 2 because I have to multiply for the highest order appearing. So the order appearing here is 2, so I have to multiply for 2. Then I have to compute the derivative at the order 2 minus 1, so the first derivative. So of this expression now I have to compute the derivative with respect to z. Then I have to compute, I have to make the limit with z that goes to 1 of all this expression. And then let's look at the coefficient. The coefficient will be 2 minus 1, that is 1. Factorial is 1. 1 divided by 1 is 1. So this is the expression that we have to do, we have to compute. So this term and this term cancel. So this is the limit with z goes to 1 of the derivative of z k plus 1 divided z minus c minus a t. Okay? Okay, now let's compute that derivative. So here we have the limit with z that goes to 1 of the derivative with respect to z of this term. Okay? And this will be the derivative of the numerator. So it's k plus 1 times z power k, and you have to decrease the order, times the denominator, minus the derivative of the denominator with respect to z, so it's 1, times the numerator, divided the denominator squared. Now I compute this limit, so I replace 1, okay? So we get k plus 1, then multiplies 1 power k, that is 1, and multiplies 1 minus e power minus at, so it's times 1 minus e power minus at, okay? Minus 1 power k plus 1, so 1 power whatever it is 1, so it's minus 1, okay? Divided 1 minus e power at squared, okay? Okay, I want to point out that you saw that maybe you may think that this formula is complicated, but if we look at this example, this is an example in which there are multiple poles. So this means that if you are doing a partial fraction, then you have to compute 1 residual for this and 2 residual for this, okay? Instead, using the inversion integral, we were able to compute only 2 residuals. So this suggests that if we want to compute the inverse transform of z transform that has a very high order at the denominator, then the inversion integral is better than the partial fraction. I want to conclude this discussion about the z transform saying that the z transform can be used to solve general difference equations. For instance, here we have a difference equation with a lot of terms, okay, that goes from x of k to x of k minus 1, and then this is equal to the sum of the input and retarded versions of the input, so delayed version of the input, okay, up to n. So we can compute the z transform of this difference equation that if you try to solve like this is complicated, but computing the z transform of this, you get this expression in which using the shifting theorem for each of these terms, you just basically get the original z transform multiplied for z power minus the shift that you are performing. So this means that on the left-hand side of this expression, you can factorize x of z, and here you can factorize u of z. And then you do x of z, you can compute x of z divided u of z, and on the right-hand side, you will have basically a fraction of 2 polynomials, and then you can use partial fractions or you can use the inversion integral. So let's do an example. So we have this difference equation. And we know that x of 0 is equal to 0 and x of 1 is equal to 1. So we use the shifting theorem and we get z power 2 x of z. Then we have to subtract the term z square x of 0 minus z x of 1 because we are using the version of the shifting theorem with the plus, okay? And then is plus 3 z x of z minus z x of 0, plus 2x of z equal to 0. So now we can factorize x of z, and we obtain that x of z times z square plus 3z plus 2 is equal, and we bring these terms on the other side. This is actually 0, and this is actually 0, but on the other side we will have z that comes from this term. And so we have that x of z is equal to z divided z power 2 plus 3z plus 2. So now we just have to factorize these two terms and compute the residuals, and so we use partial fraction, and we obtain this result once we do the computation. Okay, and then now we can invert that, and we have x of k that is equal to minus 1 power k, and then minus 2 power k. Okay, and this is our sequence for k equal to 0, 1, and so on. So we have found the x of k that solves this difference equation using the z transform and the inverse z transform. So with this, I conclude the lecture on z transform.